Astron, and he'll be talking about radio search for extrasolar CMEs and flares.
Yes, thank you very much. So that's right. My name is Konijn. I am from Astron at the University of Groningen in the Netherlands, and I'd like to thank the organizers for letting me be here today. I'm going to talk about my radio search for extrasolar coronal mass ejections and eruptive flares using the best telescope, LOFAR. Well, we already heard a little bit this week about these CMEs, especially yesterday during the Splinter session, and we heard that there's no confirmed detection of these CMEs on other stars except for the Sun. But we have figured out a couple of ways to possibly identify them, which is right here, some stellar CME detection methods. For instance, the first one, the EUV X-ray emission, the coronal dimming of them, the blue shifts in the concentric lines, some X-ray absorption, and my favorite, of course, the type 2 radio observations. It's my favorite because the type 2 radio observations are like almost conclusively, if you see a burst that looks like a solar type 2 radio burst, you can say that a CME has occurred, or at least a shock surpassing the event speed has formed. Well, we see these CMEs, we have seen them loads of times on the Sun, and this is a beautiful LOFAR image of the CME corresponding to the top right coronagraph image. And these solar type bursts, especially type 2 and type 3 bursts, type 2 bursts relate to CMEs happening, and type 3 bursts relate to eruptive flares happening. And those type 2 bursts, so most likely conflicting with the CME, takes around several minutes, whereas type 3 take around several seconds. And you can see the nice drifting burst over there, around several minutes long. The type 2 bursts drift around with 0.5 megahertz a second, while type 3 drift to 10 to 100 megahertz a second, and they both show harmonic pairs. Why do we see them actually in the radio? It's a great question you could ask. That's due to plasma emission. For example, for a CME, if the shock moves away, it's a massive shock that has formed. The shock can accelerate electrons. Those are the fast electrons. They're being shot into a very dense plasma. This dense plasma shows plasma beam-driven instabilities, which in turn can create Langmuir waves. And due to some non-linear coevolutional theory, we can create some electromagnetic transfer waves at the plasma frequency. And the plasma frequency is directly related to the density of the plasma at that point. So if you have a shock and it moves away from the star into less dense regions, you can see that the plasma frequency, so the frequency at which we see the emission, is related to the density. Density decreases as the shock moves outwards. So our entire structure should decrease. As we see in the previous image, the drifting structure we all know and love. Well, we tried to search, and with we, I mean the entire community, have tried to search for those stellar type 2 bursts loads of time, and we still have 0 non-controversial detections. There are a couple which look very promising and are super exciting, but after all these years, we have 0 stellar type 2 radio burst connections, and I'll be trying to spend my 4 years in my PhD, it's now my first year, to find these bursts, but it doesn't look super promising. If you can see the entirety of work that has been done before. Those 2 blue ones, as the years passed by, telescopes were upgraded, getting better and better. Those last 2 ones were LOFAR, and as I said before, I love LOFAR. LOFAR is amazing. What is LOFAR, you can ask? Well, if I can continue to my next slide, this is LOFAR. LOFAR is the largest, most sensitive radio telescope in these low frequencies, so around 150 megahertz, or even for the LBA siles, the little antennas you can see, going down to around 50 megahertz, even a bit below. And it consists out of tens of thousands of antennas across the entirety of Europe. It's an amazing device, and it's super sensitive. And we want this sensitivity because it hasn't been detected so far, and we need this low frequency because we think that the densities around the stars that we typically observe would correspond with the plasma frequency around our LOFAR frequencies. And not only is LOFAR amazing, but LOFAR has another amazing source, which is called LOTS. LOTS is the low frequency array 2-meter sky survey. It's created by Tim Shimwell, and it's the deepest wide field, high resolution survey at these low frequencies. And I'd like to point your attention to the wide field part of it. It's 6,000, or it will be, it's still ongoing, it will be 6,000 square degrees. So we'll cover almost the entirety of the northern sky, which is quite amazing. This shows sensitivity of the entire survey. And in this survey, we have around 3,000 pointings, and in each of those pointings is and will be observed for 8 hours. So in total, in this entirety of the survey, we have around 5 million sources, which is a lot. And we can zoom into one of those pointings, and it would look something like this. It's around 4 degrees in diameter, and you can see all those beautiful objects. Most of them are radio galaxies. So for this audience, maybe not so beautiful. But this is around what pointing would look like. And with this pointing, you can do some real science. For example, our collaborator, Cyril Tass, has looked at all the stars in a survey within 100 parsec and created a dynamic spectra at 8-second time resolution. So for each star in the pointing, for all the stars in the entire survey, we have dynamic spectra, so a frequency over time spectra, showing what the star is doing at the moment in time. This creates an unbiased view, as we don't specifically select M dwarfs or K stars or G-type stars. No, we look at all of them. And this is not a little. We have around 250,000 sources. And for each star, we have this 8 hours of data. So in total, we get like 200 years of data at 8-second time resolution, which is not a little. And I'll be trying to spend my entirety 4 years searching through all of this data, trying to give you some, hopefully, stellar type 2 burst or stellar type 3 bursts, which will be fun. One of my supervisors, Joe, he has looked at these spectra before, and he found, together with his master student, Rose Gears, about a year ago, this beautiful burst. If you zoom into the pointing, exactly that location, there's a star, and that star shows this dynamic spectra. And this dynamic spectra is cool because it shows this increase at around an hour. We can zoom into this, and this will show you the unknown stellar radio burst I will present to you today, which looks kind of cool. And why does it look cool? Because it drifts. And as I've talked to you before, the drift shows you that a shock wave is probably moving away from the source. Frequency is going lower, density is going lower, we have a drift. A drift rate with around 0.35 megahertz a second. It's super circularly polarized, around 90% so. And it's very, very bright. So you can immediately say, well, is this then analogous to a solar type 2 burst? And I will here convince you that yes, it is. Why? It drifts, that's one. It shows these substructures because it's so super bright, we can actually see them. It is at a low enough frequency we expect the density of the surrounding medium around the star to be. If this is a type 2, we can calculate the ejection velocity of the entire CME, ejection speed, which is around 1,000 kilometers a second, which perfectly falls in line with what we've seen on the sun itself. It's super circularly polarized, like 90% so this must have been the fundamental instead of the harmonic emission. And looking at the brightness and the velocity of the burst, you calculate a sort of solar equivalent rarity of this burst. We found it's around 1.5%, meaning this burst is quite rare. However, it is super bright. That makes kind of sense. But there are some difficulties with this burst and why it's not a complete slam dunk confirmation. Well, we don't see the harmonic. Those Langmuir waves can interact with each other from the plasma emission and for harmonic. And if you see the harmonic, well, we even more of a nicer confirmation of an actual stellar CME, but we don't see them here. It's only the fundamental. Why not? You could ask the question, and we ask ourselves as well. Well, the harmonic doesn't always have to reach to the lowest frequency. Our band isn't that large, as you can see. It's only 120 to 167 megahertz. So it could be that the harmonic is still above our bandwidth, so we didn't see it at all. And the harmonic, the brightness of the harmonic is related to the kinetic temperature of the plasma. So if the kinetic temperature of the plasma isn't that high, you can construct a situation where it isn't high enough, so you would be able to see it. So we can kind of explain why we don't see the harmonic. We see that it's linearly polarized. You can also ask, hey, why is it linearly polarized? That shouldn't be the case, because all of our solar observations, we've never known linearly polarized type 2 bursts. However, this is starting to be a little bit of a myth. Some recent work has shown that the type 2 burst can be linearly polarized, ever so slightly. And we initially always thought that it wouldn't be the case because of some leakage, because radio observations are fun. And sadly, the last difficult part is that we don't have multi-wavelength confirmation of this source. We'd love to have it, because if you see a burst in the radio and in the optical, well, as we talked about yesterday, then you would be very happy. But we sadly do not have this with the entire lots, because that is not possible. We only have the drifting burst itself. Well, it's a stellar audience, so what star is this burst even coming from? Well, that star right there. It's a spectral type M0 star. It's around 40 parsecs away. It's on the main sequence. It has a rotational period around once a day. Our collaborators have created some ZDI maps of this star. And we see it has some open field topology and around a 300 Gauss field strength. And immediately after finding this nice burst, we've planned and now executed our 40 hours of follow-up observation of the singular star with LOFAR, corresponding with TESS. However, TESS went into a fail-safe for more than half of these observations, so we don't have the complete corresponding TESS observations, which is of course a pity. So we have around 20 hours follow observations together with TESS and 20 with LOFAR, which we are now trying to analyze ourselves. This is one of the brightest bursts in the entire sample, and I've quickly looked at the entirety of 200 years. And I can now confidently say to each and every one of you that there's no burst in the sample as bright and as drifty as the one I showed you before. I can confidently say that there's no burst half as bright and as drifty as before, or even a quarter as bright and shows drift like before. This is really like an quite interesting one-off like event, which is just extremely luminous. Which already begs the question, we have 200 years of data on all different types of stars. Why do we only see one of these events? That's indeed an open question still. I do have some fun preliminary results. Preliminary, I mean yesterday evening. This is also in the LOTS survey, and these are two fun bursts. You can immediately see they're way less luminous. They're super dim, especially this one. We have to dance down sample it a little bit. And you can see this is Stokes V. Again, there's some sort of burst-like structure. It's no drift. There's no drift at all, but it is a stellar burst. And the other one is maybe even more fun because most of the emission in that peak comes from one singular time bin, one single 8-second time bin. So you could back the question, hey, could this then be, for instance, in type 3? Type 3 events happen at second time scales, so all the emission would be in a singular time bin. I don't know, maybe, possibly not, because we haven't seen many of them. Most likely not, but we will reanalyze the entire LOT survey at 1 second time resolution. And with the 1 second time resolution, maybe we can find other types of structures. Signal to noise would increase with about a factor of √8, so maybe that would help. But this is still ongoing, and I will hopefully present in the next Cool Stars some more interesting bursts. But with that, I will leave you with my summary slide. I'm now in the process of analyzing the entirety of the years of data at 8 second time resolution. We have found a stellar radio burst analogous to a type 2 burst, indicative of a stellar CME, and the publication is on the way, led by my supervisor Konijn, and we have 40 hours planned, which hopefully shows something. Thank you.
Start off with one. Oh, here we are, right here.
Yeah.
Yes.
Okay, Rachel Austin. It was a nice talk. So you presented evidence for why you think it might be a type 2 burst. What is the evidence for why you don't think it's cyclotron burst?
That's a great question. Well, we don't think it's like cyclotron maser emission, and that's mostly because of the drifting structure. And this high circular polarization, however, cyclotron maser emission can show this as well. It is mostly due to the drift of the burst. Yes. Yeah.
Right here, there we go. Good wave in the back. I appreciate that. Tell us your name and ask your question.
Hello, this is Leonardo Guardado from Leibniz IP. Thank you for a great talk. I have a small question. So you said that you have looked at the source also with some test observations, perhaps not the one that you wanted. Can you tell us something about the flare activity of the star? So does it flare very often? You know, their flare rates, what are the flare properties of the star?
That is a great question, and I'm sorry I do not know this off the top of my head. I know it flares regularly enough. It doesn't flare. It does not flare at all. But I don't know the specifics of the flare activity. I will look into it. Yeah.
Last question here. I have a question as far as how do you do the multi-wavelength follow-up when you see something, or is it just you hope that it's been caught by tests?
Exactly. We hope that it's been caught at the same time. So we try to find some candidates to look at with this entire survey. If we find an interesting star candidate, then we'll do the multi-follow-up observations. Yes.
Thank you. Thank you, speaker. Right, our next speaker is going to be Philip Lucas from University of Hertfordshire.